Hello, everyone. I'm Mihika. I'm currently a senior at Agnes Scott, majoring in astrophysics and economics. This summer, I was a part of the NAC cohort at Socorro, New Mexico. My project is VLBI imaging of VLASS detections, and I was mentored by Dr. Tony Beasley. So the VLA Sky Survey, it has been able to detect many interesting objects. Here is a look at some of the objects that it's been able to detect. And this has led to several large projects as well as collaborations. So we've seen an increasing importance of such uniform large surveys. So we wanted to propose a targeted all-sky survey with the VLBA, which has 1,000 times more resolution than the VLA. Our motivation for this, it comes from the fact that such a survey would give us extraordinary scientific outcomes, ranging from detections of gravitational lenses, creating emission models, milli-arcsecond images of radio sources, to adding a list of calibrators to the phase reference calibrator catalog, which are used for geodesy and astrometry. So all in all, many, many scientific results. So to start off, what we did is we proposed 4 pilot epochs in different parts of the sky. And with this, our main goal was to use the VLASS data as sort of like a cutoff to find out whether we can use that to do source selection. And then, of course, a bigger part of our project was to make sure the survey came to a point where it was feasible to be proposed, that it didn't take 20,000 hours. So here is a look at what the source looks like in one particular field. So what we did is we started with the VLASS data, and we got a list of all the sources in one particular field. Then we put a floor cutoff of 1 millijansky for the flux, and we made sure that all the sources that we detected were compact such that the peak to the total flux ratio was 0.4 or more. And so here we can see per degree, we actually detect about 50 sources. We also kept track of what we call bright targets. These were targets which had a high flux, and those could be used as calibrators when other calibrators were not available. So once we had a list of all the sources, we put them through a scheduling program called SHED, and that gave us an estimate of how long the survey would take. So we found at the beginning it would take about 18,000 hours, which is a lot of time. So to reduce this amount of time, we had to increase the antenna efficiency. Now, antenna efficiency is the ratio of the time spent recording the sources over the total time that the survey takes. So the total time also involves some of the slew timing, which is the time that the antennas take to move and settle on the particular object. So we found that the slew time, to decrease it, we could use a special program called the simulated annealing program. What it does is exactly what there's on the screen. If you give it a list of random sources, it will optimize the path that the telescope takes to go through all of these sources, thereby decreasing the time that the telescope takes. So overall, we found that it cuts the time in about a half. And so we tested this on a bunch of artificial sources, and it worked well. We found great results. And so when we tested this on our source list and put it through SHED again, we found that there was actually no difference, which was a little bit weird. So upon further investigation, we found that's because SHED has some default parameters, and it had a default parameter of 10 seconds for the slew time. So we looked at the antennas to detect whether they actually needed the 10-second slew time, and we found that the antennas generally required less than 5 seconds. So a lot of our inefficiency came from this part. And so when we ran the 4th epoch at the end of July, we made sure to take away that fixed parameter, the default parameter of 10 seconds slew time, made it to be 0 seconds, and then we ran it again. The antenna was still very efficient. It took less than 5 seconds to slew, and we found that the efficiency actually increased from 62% to 80%. This cuts our survey time by a lot. This was the technical aspect of the survey. Moving on, we have the imaging. So here are two of the objects that we detected using the VLBA survey. So here it's a little bit clear to see that these objects that we want to detect are not centered. That means it has a positional offset, which is, it can be easily corrected, and it's a systemic effect. We also found that amongst all of the sources that we put in, we actually see about 15% survival rate, as in 15% of all the sources actually show up on the VLBA. Some of the flux, when we looked at the flux of these objects, we found that our data was affected by bandwidth smearing. So that artificially lowered our flux by 30%. But when we did correct for it, we found that the flux was within 50 to 100% of the VLASS detected flux. So we were happy with that. Here is a more closer look at one of the objects. So these are high resolution objects, and we've only gone through some of them. There are many interesting results to come. For example, here we see a very compact object. This could be a part of the VLBA calibrator survey. So we can add to the list of the calibrators that we already have, which then is a great scientific outcome that we mentioned earlier. So it proves that, you know, the VLBA survey actually has a lot of scientific outcomes. This is a very interesting result. So here what we see is that below 7 sigma, this is the signal to noise ratio from our epoch A observations. And below 7 sigma, we see that most of the objects we find are not real objects. So the real objects that we actually were able to see on the VLBA were all above 7 sigma, which is a lot. So that probably means that the 1 millijansky cutoff that we had initially was far too low, and maybe a 3 millijansky cutoff makes more sense. So our results and conclusions from this is that we can now increase the array efficiency even further, from 80% to 90% by using the simulated annealing program. We should also increase the flux cutoff to 3 millijansky instead of the 1 millijansky. And so far, we've been calibrating in AIPS, but we're moving that to CASA, also taking care of bandwidth smearing as we go on. And then we observe typical noise and RMS, which we expect. The survival rate fraction is 15%, and we observe a positional offset because of VLASS. However, that can be very easily corrected in CASA. So this is where our survey stands as of right now. So we would be able to actually survey 30,000 square degrees of the sky. And with a 3 millijansky cutoff, that is 25 sources per degree, which is half of what we saw before. However, that's still plenty because that amounts to 750,000 VLASS sources. And with our survival rate of 15%, that means we'll be approximately be able to see 127,000 VLBI sources. It's not linear, however, it's still a very good approximate. The big thing is though, we were able to reduce the survey time from 18,000 hours to 2,700 hours, which is a very reasonable amount of time to ask for such a large survey. So our ongoing projects and our future steps are, we're working on a CASA pipeline for imaging as well as calibration. And once we're done with the pipeline, we would like to analyze the images that we have seen to make sure that they fit with the science goals of our project. And the next steps would be to take care of all the other technical aspects of the project. For example, the data management, because this is going to be a large amount of data coming in, and to make sure that we have the survey at a point where it can be reasonably proposed, maybe by next year. So before I end, I would like to thank the NAC program, NRAO, Lindell, Tiara, JJ, everybody who's organized this, and of course, Tony for being such a fantastic mentor. Thank you very much. I will now take questions.
So nice talk, Mihika. I wanted to ask about the annealing approach, which seems really cool. It looked from the figure you showed that you were currently working with kind of a square patch and increasing the efficiency of observation over of sources within that patch. Is this something that you could generalize into like a longer stripe? Like just have a really, long continuous observation and kind of anneal your way along a stripe in the sky as it passed overhead?
That's a great question. So that's definitely something that we were kind of working on and like looking at. So we tested the annealing program on a set of artificial sources. So like a circle or square, and it did exactly what we wanted it to do. It did actually optimize the path. So in theory, it should be able to optimize even if we're doing a long patch of sky. It should give us the same results. However, we haven't tested it yet. So we will be testing it thoroughly and maybe adapt it to make sure that it does what we want it to do, so that it does give us an optimized path as we go through the entire sky.
Thanks.
Well, thank you so much, Mihika. This was a really good talk.
Thank you.